Welcome to lesson 11.2. In this lesson, we're going to take a look at single replacement reactions. So much as it sounds, a single replacement reaction involves an element by itself replacing an element that's in a compound. So here we see we have A plus BC, and it's going to react to form AC. A is now taken the place of B, and B is now an element by himself. So B was replaced. When you look at the reaction, and you look at the reactants, if A is a metal, then A is going to replace the other metal in the reaction. Remember, metals are written before nonmetals. So in the compound BC, B would be the metal. So A replaces B, and now we have compound AC plus B. Here's an example: sodium plus potassium chloride. Sodium is a metal from the left side of the periodic table. It's going to replace potassium, and now you're going to have sodium chloride and potassium by himself. If A is a nonmetal, then it would replace the nonmetal. Again, remember, metals are always written first. So in compound BC, C would be the nonmetal. So if A is also a nonmetal, A will replace C, and we'll end up with compound BA and C by itself. The example there, chlorine plus potassium bromide. Chlorine is a nonmetal, so it's going to replace the nonmetal bromide and potassium bromide. You'll end up with potassium chloride plus bromine. That brings up what we call our solubility rules. Solubility means what will dissolve. So usually in our single replacement reactions, we'll be working with ionic compounds, a metal and a nonmetal. When these take place in water, which they oftentimes will, we use what we call our solubility rules to determine the states of matter. On the back of your periodic table, you'll see our solubility rules, and it'll be helpful if you get those out now and reference it when we talk about them later. So on the back, at the top, we have 6 rules to follow. The more you read these and the more familiar with them you get, the easier it'll be for you when test time comes to recognize what are soluble and what are solid. Let's take a look. Potassium reacts with water. So we write potassium, that's K by itself, and water, which is HOH. I know you're familiar with seeing H2O, but I'm going to let you know right now, I think it's a lot more helpful, as strange as it may be, to write water as HOH. This allows us to see the 2 ions. We have a hydrogen ion, H+, and a hydroxide ion, OH-. It's still H2O, it's still water, but I think it really helps when we're writing and balancing our equations to see it as HOH as compared to H2O. You're welcome to write H2O, but again, I think it'll be more helpful if you write HOH. All right, first step, we have to predict our products. We have potassium, which is a metal, and HOH, which is an ionic compound, or very similar to an ionic compound. H, hydrogen ion, is acting as our metal. It is definitely our cation, so K will replace H, and we'll end up with KOH, potassium hydroxide, and now hydrogen by itself. We want to balance and make sure that everything has the proper number of subscripts. Potassium has an oxidation state of +1. Hydroxide has an oxidation state of -1. And I check the back of my periodic table, the polyatomic ions down at the bottom, and I find hydroxide with its -1 oxidation state. They're 1 to 1, they balance out. Again, remember to erase your charges. Hydrogen is a diatomic, so I'll make sure I write H2. In order to balance this then, I have 2 H's So I put a 2 out in front. Again, had I written H2O, I might be confused as to how many H's I have. But I know that I have 2 H's. I'm just going to count the hydrogen ion as H because I will keep the H with the O as part of my hydroxide ion. I now have 2 hydroxide ions, 2 OHs, so I'll place a 2 in front of my KOH. Now I have 2 hydroxide ions in this compound. But it also means I now have 2 potassiums. That's pretty easy to solve. I will add a 2 in front of potassium over here. All right, looks like we're all balanced. 2 hydrogens, 2 hydrogens, 2 hydroxides, 2 hydroxides, 2 potassiums, and 2 potassiums. Finally, I need to use my solubility rules and figure out what states of matter I'm working with. Potassium is a metal, so he's going to be a solid. H2O, that's water. That'll be a liquid. We should all know that one. Potassium hydroxide. All right, here's my first instance where I need to find something with a solubility rule. I'm going to call this one aqueous because of rule 2. So we're going to read through my rules. Nitrate, that's NO3 -1, and acetate, C2H3O2 -1. These salts are soluble. That means they will dissolve. That means aqueous. But KOH is neither of those two. So on to rule number 2. Group 1A, these are alkali metals, and ammonium, NH4 +1. These salts are also soluble. Well, potassium is a group 1A alkali metal. So this is an aqueous compound. It is soluble. It will dissolve in water. Aqueous it is. All right, there we go. Rule 2 is applied. KOH is aqueous. Finally, elemental hydrogen. We're all familiar with that one as a gas. All right, there we go. We've written our first single replacement reaction. Let's try another example. Barium reacts with aluminum sulfate. All right, so barium reacts with aluminum sulfate, sulfur with an 8. And you see, anytime I see that ATE or an ITE, I know I'm not working with elemental sulfur, that'd be sulfide. Instead, I need to look on the back of my periodic table and find sulfate, SO4. Okay, barium is a metal, aluminum is a metal. Barium will replace aluminum in this reaction. So barium sulfate and aluminum now by himself. There's the single replacement. Barium replaces aluminum. Let's balance this bad boy. It starts with subscripts. Aluminum has an oxidation state of +3, sulfate -2. Again, I think the easiest thing to do is cross over. So I bring the 2 down behind aluminum. That's going to give me a total of +6. And I bring the 3 down behind sulfate. Don't forget your parentheses. I need 3 of the entire polyatomic ion sulfate. That gives me -6. +6 and -6 cancels out. We now have a properly written aluminum sulfate. Erase those charges. We don't have an ion. We have a compound. On the other side, barium has a +2, sulfate has a -2. Again, that's a 1-to-1 ratio. There's no reason to cross over. They're going to cancel out, so we're good. Erase those charges. We don't want to have those in the final answer. Neither barium nor aluminum is one of our diatomics, so no reason to write a 2 after either of them. They're fine by themselves. So our next step is to make sure we're balanced with coefficients. I'm going to put the 3 in front of barium sulfate. I have 3 sulfates over here, so I'm going to need 3 sulfates over here. Good. Sulfate, SO4, is now balanced. I have 3 bariums now on the right, so I'll put a 3 in front of barium on the left. Good. Now barium is balanced. Finally, I've got 2 aluminums on the left. I can solve that by putting a coefficient 2 in front of aluminum on the right. Now I have 2 aluminums on both sides. My equation is now balanced. Final step, add in those states of matter. Barium is a metal by itself. All metals, with the exception of mercury, are solid, so barium is solid. Aluminum sulfate. Let's look for a rule. Rule number 4. Most sulfates, this is a sulfate, are soluble. There are a couple of exceptions, for instance, barium sulfate, lead sulfate, and calcium sulfate. Aluminum is not one of those three, so that means it is soluble. We'll put aqueous, which means it's been dissolved in water. On to barium sulfate. We'll use the same rule. Rule number 4. Most sulfates are soluble, except barium sulfate, lead sulfate, and calcium sulfate. So in this case, we're going to put soluble. This time we're going to put solid for not soluble. This one will not dissolve in water. It will remain a solid. Finally, aluminum is a metal by itself, so it will also be a solid. There we go. We've written we've used our solubility rules to write a couple of chemical reactions with single displacement. There's one more little trick also on the back of your periodic table. Sometimes metals will not replace other metals. We need to look at the back of our periodic table. In order for one metal to replace another, it must be more reactive. You're going to be given a list on the back of your periodic table of the most reactive, that'd be lithium, all the way down to the least reactive, that would be gold. How this list works is only the element higher up can replace the other element. So if lithium is by himself, Li is by himself, he will take the place of any other element that's present. But if the element by himself is lower, for instance 10 could not replace anybody higher than himself. So if 10 by itself were reacting with, let's say, iron nitrate, we would say no reaction because 10 is lower on the reactivity series than iron. Let's do an example. Hydrogen reacts with cupric hydroxide. And hydrogen is one of our diatomics, we'll put H2, reacts with cupric hydroxide. Cupric has a positive 2 charge, hydroxide has a negative 1. So make sure we put parentheses around a hydroxide and a 2 after it. Erase those charges, we don't want to keep them in the final reaction. Let's take a look at our reactivity series. Hydrogen is on there, and indeed he is 1 above cupric. He is just above copper, so yes, hydrogen will replace copper. Copper will now be by himself. H replaces copper, he's now HOH. That should look familiar, that's water. H and OH each have a positive 1 and negative 1 oxidation state, so they balance out. We don't need any subscripts. We do need to put the coefficient 2, because we have 2 hydroxides and we have 2 hydrogens. Finally, we go back in and add our states of matter. Hydrogen is a gas. Cupric hydroxide, we'll need to find a rule for that. I went down to rule number 5. Most hydroxides, OH negative 1, are insoluble. Calcium hydroxide is an exception, but cupric hydroxide is not that exception. So cupric hydroxide will be solid. Copper by himself is solid. HOH, we should all recognize that as water. That's a liquid. There we go. Let's do another one. Sodium reacts with potassium chloride. Okay. Sodium by himself is Na, reacts with potassium, KCl. Let's check and make sure we have a balanced subscripts. Potassium is positive 1, chloride is negative 1. No reason to write anything, and positive 1 and a negative 1 will cancel out. Let's erase them. Reaction, all right, sodium is a metal, potassium is a metal. Sodium will attempt to replace potassium. Let's check our back of our periodic table, our reactivity series. and see if sodium is higher up than potassium. Taking a look. Potassium is the second highest listed metal. Sodium is down there at number 5. Sodium cannot replace potassium. Sodium is not higher than potassium. This reaction will not happen. We put NR for no reaction. This reaction will not happen. That doesn't mean we don't need to finish writing our states of matter though. Sodium is solid. Potassium chloride is aqueous. That's rule 2. Potassium is an alkali metal. Those are almost always going to be aqueous. But again, we write NR. We have no reason to balance or write any products. No reaction will happen. Sodium is not strong enough to bump off potassium and potassium chloride. No reaction will occur. Nonmetals also have a reactivity series. It's not listed on the back of the periodic table, but it's on the front. For the most part, the nonmetals you have reacting will always be your halogens. So how reactive they are is simply the list that you have on the front of your periodic table, the order that they appear on the periodic table. So fluorine's up at the top. He is the most reactive, followed by chlorine, followed by bromine, followed by iodine, followed by astatine. Let's do some examples. Bromine reacts with sodium chloride. All right, we have bromine plus sodium chloride. Here's bromine by himself, sodium chloride. Sodium has a +1, chloride has a -1. Again, no reason to write anything, they balance out. Bromine is one of our diatomics, so don't forget to put that in 2. Will this happen? Well, bromine's a nonmetal. Chlorine is a nonmetal. Bromine will attempt to replace him. We look at our reactivity series, which is just like the front of the periodic table. Chlorine is higher up than bromine. No reaction. Bromine cannot replace chlorine. Chlorine is more reactive. Doesn't mean we don't have to add in our states of matter. Bromine is one of the 2 naturally occurring liquids on the periodic table. So we put liquid. Sodium chloride, aqueous. Sodium chloride, that's table salt. Hopefully we're all familiar with the fact that sodium chloride is soluble. It will dissolve in water. So to symbolize that, we put AQ for aqueous. Let's try another one. Fluorine reacts with sodium chloride. Fluorine and sodium chloride. Again, sodium and chloride, they each have a +1 and a -1. No reason to write any subscripts. Fluorine is also one of our diatomics. So there's our 2 for fluorine. This time, fluorine is the most reactive halogen, so it definitely will replace chlorine. So we'll end up with sodium fluoride and chlorine by himself. Let's make sure our subscripts are balanced on our product side. Sodium is +1, fluorine is -1. Again, no reason to write any subscripts. +1 and -1 cancel out. Chlorine is one of our diatomics. So that gives us Cl2. Now we have to go back and balance for coefficient. Well, I've got chlorine over here and 2 chlorines over here. So I'll put a 2 in front of that. That works out well. Now I have 2 sodiums. I'm going to need to add a 2 over here for 2 sodiums, but that takes care of fluorine as well, which has 2 on this side. Now it has 2 on this side. Wonderful. We're all balanced. Finally, put our states of matter. Fluorine is a gas. Sodium chloride is aqueous. Sodium fluoride is also aqueous. You can check your solubility rules if you're not as familiar. That would be rule 2. Group 1A, alkali metals, that's sodium, are soluble. So sodium fluoride, definitely soluble, plus chlorine, that's a gas, chlorine gas, there we go. So here's your homework for this evening. First step, identify. You have 3 types of reactions to work with now. Are you working with a synthesis, a decomposition, or a single displacement reaction? It can be single displacement or single replacement. Either way works. Secondly, write your balanced chemical equation by predicting your products and add your states of matter for each reaction. So for the first one, you have lead plus zinc acetate. What type of reaction you're working with? An element plus a compound. It looks like a single replacement reaction to me. This could be quite important because when you're identifying your states of matter, remember we only use your solubility rules for single replacement.